at this position. If at a slightly later time point, a structure that's producing the backscattering signal here has moved, let's assume a red blood cell, for example, has slightly moved here by a fraction of a micron, fraction of a wavelength, it will produce a phase corresponding to 2 times k, same wave number here, times Z2. So if now we take 2 acquisitions at time t1 and time t2, we can compute the difference of the phase signals here, the phase difference, which is proportional to the change in position. Yeah? So the phase difference encodes the position change here, proportional to the wavelength. We can now take this and turn it around. We know that velocity is position change over time. Then we can just fill in this over here, convert wave number to wavelength, and we end up with velocity then equals something that's proportional to the phase difference, and wavelength here indirectly proportional to refractive index, and indirectly proportional to the time elapsing between the 2 acquisitions. Yeah? The time between T1 and T2, that's tau over here. So by measuring the phase difference, we can convert this into a velocity in beam direction. Now we can do these phase difference measurements at different time scales. Yeah? Depending on which time scale we look at, people have given this different names. But in the end, it's all the same thing. If the time difference is on the order of microseconds, so that's on the order of the time elapsing between axial scans, then this would be like we take 2 acquisitions, one after the other at the same position in a B scan. So this is the phase tomogram here again, just like we saw it before. Then we compute the phase difference for every position, and then we can convert this into velocities, and this is called Doppler OCT, similar to Doppler ultrasound imaging. If we compute these phase differences at a slightly different time scale, at a longer time scale, so we take a time scale on the order of milliseconds, that's the time it takes typically to acquire an OCT image. That means we compute another phase difference between the same position, but from one OCT frame acquisition to the next frame. Yeah, compute the phase difference between these 2 images because the parameter tau between the 2 acquisitions is now longer. We get access to a different dynamic range of velocities, and this would be the case, for example, for OCT elastography, like we have seen it yesterday, or if we threshold OCT elastography images and convert them into binary images, so-called OCT angiography, which is used a lot in the clinic today, and I will show you some examples a little bit later. So then we would be susceptible to a velocity range on the order of micrometers per second, so a rather slow flow like or motion like we have it in capillaries. Good. Let's see how we can actually use this. So here we see a model of the eye, and if, for example, we have a look at the back of the eye here, and we perform scans of the papilla here, where the retinal blood vessels are getting into the retina, blood is also flowing out of the retina again. We get intensity or activity images that look like this, that give us an impression of the structure of the optic nerve, where we can see some of the neural tissue here, and some blood vessels over here. Not too much to see here, but if now we perform this phase analysis and just compare the phase signals or compute the phase difference between repeated axial scan signals, then we get images like this. Yeah? Here on this color map here, green denotes zero displacement, zero velocity, and then it goes up to plus and minus 20 millimeters per second. And we see that we see some flow here in these blood vessels, which are not really visible in the structural image here. If we do this in a 3-dimensional scan, we can nicely see some blood vessels here. This is at 100 kilohertz, and if we, for example, take cross-section at this position, we can, in single vessels, convert the velocities into flow rates for given vessels, which, for example, for these 3 vessels are around 10 to 30 microliters per minute. If we speed up our OCT device and now go from 100 to 200 kilohertz, remember we are now tweaking the tau parameter, we can now measure even faster velocities, and it's easier to see these central regions here of the close to the central retinal artery or the central branching here, which sits on top of the venous vessels here, shown in blue. We can also use this to perform time-lapse imaging of pulsatile blood flow, for example, and convert this into some quantitative numbers. There are also other things going on because the eye is a system that contains lots of forces working against each other. So we have IOP, like pressing the eye in shape here from the middle, but we also have pulsatile blood flow in the outer shell, in the retina, and also in the choroid, which produces a pumping motion of the ocular tissue here. And if we look at this a little closer here in the back of the eye, then we see that we actually get some kind of pumping from the choroid and from the retinal vessels over time. Now we can take our OCT machine again and quickly scan the retina a few times and then compare again the signals, the phases at two different time points and produce displacement maps. Now we don't just look at the blood flow, have the how much have the blood cells moved, but because we are scanning rather slowly, we can actually measure very fine displacements of the tissue over time. And here we see an example. So we see the structural image here of, for example, a mouse retina here, and we see the blood vessels, these bright guys up here. In the structural OCT image, so here brighter means more light is backscattered, and darker means less light is backscattered. This is the phase difference image for one given time point, showing us by how much has the tissue been displaced or not been displaced relative to the retinal pigment epithelium, the RPE, which would be located here. So at the RPE, we've chosen to set this to 0, and then you see the relative motion of the tissue with respect to the RPE. You see here in the choroid a lot of displacement, but also around the larger retinal vessels we see, not only the vessels here, but around the vessels we see that the tissue is being displaced. And if we not just do this between two images, but between a series of images, so here, for example, we acquired 2,000 images, over time we see this periodic pattern appearing as the blood is pumping pulsatilely through the retinal and choroidal vessels. And for each of these locations here, for each given location in this OCT image, we can now analyze by how much is the tissue moving, and then perform a frequency analysis to for example, see the motion patterns in different locations of the retina. And here, for example, we see two major components, one arising from blood pulsation with some harmonics here, and here the right-hand side here is a zoom in into this low frequency box here. This is from respiratory motion. And we believe that such data can be useful for performing some kind of elastographic analysis, and this is actually the subject of a research project we are having with the Nicholas Copernicus University here, where we try to make some useful data out of these elastography images of the eye. Here I'm just showing, because so far we've looked at only two-dimensional scans, this would be a fundus map of displacements around the papilla in a red eye. We analyzed, for example, how different IOPs influence the modulation patterns here, and for comparison here, this would be an OCT angiography image where we see the superficial retinal vessels in blue, and then the intermediate plexus or the retinal vessels deep in the retina in green, and then the choroidal vessels here in red, for example. Okay, now let's quickly switch on topic and go from motion contrast to polarization contrast. And the first thing we want to look at is birefringence. birefringence is it's a property, a polarization property that is often observed in fibrous tissues, which are made out of elongated filaments, and these can produce so-called birefringence, which is a different refractive index along the fibers versus perpendicular to the fibers. Can be different kinds of fringence, but anyway. And the difference of these two refractive indices is called the birefringence. For example, in fibers or in muscle fibers, we can observe this. And if now we shine differently polarized light through this fiber bundle here, for example, because the speed of light, the refractive index, is different for light polarized perpendicular to the fibers as compared to light polarized parallel to the fibers. The light will travel at different speeds and will be subject to a delay, so-called phase retardation, which is proportional to the birefringence and also to the things traveled through the tissue. And this retardation, as well as the orientation of the tissue, of the birefringent tissue, these are properties that can be measured by so-called polarization-sensitive OCT. So OCT including also additional polarization components. And here I'm showing an example of the brain stem. So this would be like the location in the back of the head here. This is of course not in vivo. This is a photograph. This is the reflectivity image showing us how much light is coming back from which location, and the retardation image showing us where we see more or less retardation here, and the X orientation showing us the orientation of the birefringent fibers, which allows us some kind of tractographic imaging here. Another example of the brain, some birefringent structures here. So we used our polarization-sensitive OCT machine to image a brain sample of an Alzheimer's patient with some amyloid beta plaques in the brain, and these can be distinguished by OCT without any staining and intact tissue here. And we also then were excited by this and got some funding to image some mouse models where we also observed in the retina some structures that actually changed the polarization, and which reminded us of these structures we saw in the brains of human Alzheimer's patients earlier, but we also observed this in some mice, and actually in this case some of this was related to these amyloid plaques, but there are also other structures that change the polarization of light, like for example melanin pigments. Another example of the use of polarization-sensitive OCT here is birefringence imaging. So of the retinal nerve fiber layer, where, for example, colleagues have shown that you can see differences between the birefringence of the retinal nerve fiber layer produced in glaucoma patients compared to healthy subjects. Here's another example. Yesterday we saw a few presentations about keratoconus in OCT. You can also, for example, image the polarization properties of keratoconus, which are drastically changed as the layer structure becomes different. Another topic where we can use polarization and OCT, so-called depolarization. This refers to the change of the polarization state, which depends on location. So different locations within the tissue would produce slightly different polarization states, and we can analyze this with polarization-sensitive OCT. One structure that we've seen before that can depolarize light is melanin or melanin pigments, and these are located in many structures in the eye. For example, in the pigment epithelium of the iris, in the choroid, but also in the RPE, the retinal pigment epithelium. And we used polarization-sensitive OCT to actually measure this polarization change in the retinal pigment epithelium. So here you can see this retardation image, where you can see that blue means no change in polarization, and green you see that actually in this layer, actually there's quite a lot going on. And we converted this to a property that shows us how much depolarization do we see in different locations. The red here means no change, or very little change, and a lot of depolarization going on, for example, here in the retinal pigment epithelium. This can then be used in before. So here we just saw a healthy subject. Here we see the retina clearly is very disturbed. This would be a case of dry AMD with geographic atrophy, so the photoreceptor layer, but also the retinal pigment epithelium are drastically destroyed. So this would be the reflectivity image that you would typically get from an OCT machine. If you combine the polarization contrast with the reflectivity image and overlay which of the structures shown here are actually depolarizing the light, then you can see here the retinal pigment epithelium or whatever is remaining in this patient here in red, and pigmented structures in the color here in green. If you do this not only for one image but for many, you can convert this into a thickness map of the RPE thickness of the RPE, and where you can nicely see zones of atrophy, so where the RPE is gone, and then also hyperpigmented regions around this. And our colleagues at the Department of Ophthalmology actually analyzed different shapes of other structures of drusen's in early AMD, which are these subretinal or different kinds of deposits under the retina or the retinal pigment epithelium, and analyzed how they might differ for different cases. And this contrast can also be used, of course, to segment the layer, the RP, for example, based on its depolarization properties, and then perform thickness maps like this. Of course, you can also generate something like this based on just these images, the intensity images, but yeah, then you may be uncertain what is actually the RPE or what is maybe not it. We then try to also get some quantitative information out of this by first analyzing how does depolarization, so-called degree of polarization uniformity, how much is the polarization changed with the concentration of melanin and melanin phantoms, with particles sized similar to the pigments in the retinal pigment epithelium in humans, and then also analyzed differently pigmented rats and tried to get a correlation between depolarization and the pigment density there. And we think that this could be, because there's a quite nice correlation, this could be a quite good parameter for non-invasively assessing the pigment density in situ and in vivo. Another way to do this that we tried, and now we'll come back to what I said on one of the first slides, is visible light OCT or spectroscopic OCT, where actually we use a very broad wavelength range from 400 to 700 nanometers, and then analyzed actually scattering changes based on least scattering within the pigmented structures here, and converted this into some contrast here. As a last set of images, I just want to show you some multimodal imaging, not only in the eye but also in other structures that we have performed very quickly. So here, this is one of our prototypes for imaging small animals, which actually provides polarization contrast, but also blood flow and the typical morphology contrast. And we've used this to image different animal models, where we, for example, can see or can trace over time a repeated imaging the formation of new vessels in OCT and geography images, or the pigmented structures moving through the retina over time, and correlated this to histology as well. We also analyzed different mouse models of AMD, for example, for pseudodrusen, where we have some deposits in the retina. This is another prototype we developed for imaging brain samples. So we see one example here for imaging amyloid beta plaques here, these structures here, compared to histology in Alzheimer's disease. And we also investigated different brain tumors, which, as you can see here, have slightly different morphologies. And as the last example, we see here some brain pathologies that we image based on how the light is scattered from the tissue, so how it is scattered in different directions, which gave us some additional contrast, and also for classifying different types of brain tumor samples that we got directly from brain surgery, from neurosurgery department on their way to the neuropathology department. So now I've seen many images and hopefully learned a lot about OCT. So I hope I could show that. I hope you learned a little few new things about how OCT works and how we can add additional contrast, for example, by performing time-lapse imaging or polarization-sensitive or spectroscopic imaging. And I believe at least that some of these methods will be useful for adding additional contrast and hopefully also clinically useful. I would like to thank all of our collaborators and the group, and of course I would like to thank you for your attention. I'm happy to take any questions.
So thank you very much for this very comprehensive presentation about OCT. We have time for a few questions. Okay, so I have one question. OCT are performed widely in the eye clinics, right? So like tens of millions of scans per day. So my question is, which of those techniques you think will make it to the clinic? Because now it's only structural imaging, right, and angiography. This Doppler OCT never made it, right, to the doctors. So what's your opinion?
Yeah. So as I said, so I think so far what's been used in the clinic is structural imaging and angiography imaging, which does not really require any changes to the optical setup. Polarization-sensitive OCT may also be useful, but it requires additional components in the setup, so it's not something that can be implemented in existing systems. Doppler OCT, on the other hand, is something that could be useful. It has been shown that it can distinguish, for example, blood flow differences in different patient groups. But I think what's still missing are large-scale clinical studies that actually show the relevance. And I think as long as this has not been done by experimental systems, we will not see it in clinical systems.
Any more questions?
Thank you for a very nice presentation. I was wondering, is staining used for any application for the OCT?
So typically not, but we've done it, for example, using visible light OCT, so similar to white light microscopy, you can use the same stains to generate additional contrast. We also stained and added a fluorescence channel to OCT to get additional information, for example, but usually it's not done. Usually you don't need contrast agents for OCT.
Is it maybe you see any future application for some structures that are not visible at the moment? I'm thinking maybe a crystalline lens structure in more detail.
Well, I don't know if we will see this today, but you can also use the crystalline lens with OCT. I think Eric has shown it 2 years ago. So I think maybe yes. So for example, also for OCT angiography, compared to fluorescence imaging or fluorescence angiography, you cannot detect edema, for example, or slow flow. So that's something that OCT cannot do yet, and that's maybe something where contrast agents might help.
Thank you very much for the nice presentation, really beautiful. I have a question. You showed us very nice images how you can detect basically a disease that is already apparent to the eye and the macrostructure. Is any of these techniques sensitive to prediction before you can see it?
I would say yes. So that's something that, in particular now, that there's a lot of data has already been acquired, and deep learning and big data analysis have become more and more prominent. That's something that's not going on. So that based on very subtle changes, you will be able to predict how maybe a disease will progress or which kind of treatment to choose.
From your experience, which of the shown techniques do you think is one of the hottest candidates?
You mean of those? I like to know.
question over here.
Yes.
Thanks for the nice overview. In the field of myopia control and myopia progression, the field is using OCT, structural OCT, to look at changes of the choroid layer. But the thickness changes are small, maybe 10 microns of expansion or shrinkage of the choroid layer. And there's always a question when we look at this choroid data, is it real, or it's right at the limit of the axial resolution of these commercial OCT systems. So, as an expert, in your opinion, like in the next 10 years, should we expect things to improve? Is there a hope that we'll be able to more accurately measure these small changes, or is the technology kind of mature for that, and what we have now is as good as it's going to be?
Yeah. So I think that the issue with imaging the choroid, as we've seen in some of these images, is that because the light has to pass through the retinal pigment epithelium first and then through the choroid, which contains all these blood vessels, which attenuate the light beam, and then also the pigments in the choroid, which may differ from eye to eye, depending on how darkly your eye is pigmented. You may or may not see the end of the choroid. And this can be improved by maybe choosing longer wavelengths for imaging, or by averaging several acquisitions, which is something that's getting more and more done as devices are getting faster and faster. So I would assume that maybe this will become better. But the question for choroid imaging is also how stable is the thickness of the choroid over time. So that's something that's, I guess, under debate at the moment.
Okay, so one last question from you.
Just a short question. Following Nida's question, how do you think is the OCT at longer wavelengths, like 1700? Does that make sense for eye imaging? Any applications to see through the sclera?
Well, so if you use light at longer wavelengths, then a lot of the light will be absorbed by the water in the eye as it travels through centimeters of eye. So you would have to use great eye. So I think it's possible to perform imaging of the, if you talk about imaging the sclera at the posterior pole, if you want to image the sclera at the anterior eye, of course that's always possible. And I think there it makes sense to use longer wavelengths.
Okay, so let's thank our speaker.